Okay, so first of all, thank you, Enrique, for giving the chance to give this talk. I know it's 11, so we are all thinking about coffee, so I'll try to not bore you too much. And as Enrique was saying, like my name is Josu, and I will be talking about advances in low overhead error correction, so trying to do quantum error correction with less resources, basically, which is one of the main challenges of the field right now. So I will mainly speak about two works that we've done with all these wonderful collaborators, and you can find them on the archive. So I will try to not go super in deep into them because my main idea today is to give you a glimpse of what we are trying to do with this stuff. So why do we need QVC? We've been hearing about T1s, T2s, and stuff. But when we want to go like full-scale quantum computing and we want to do like trillions of quantum operations, it seems that it's not possible to construct qubits that act as quantum computers. They are more interested in, interacting with environment and lose coherence and, don't store the information. So quantum error correction was conceived for that. And let's say what's the state of the art. So for example, one family of codes that is very famous is called the surface codes, which are planar codes, which is one of their advantage. So you can construct them by using a 2D lattice with nearest neighbor connection. This is a very relevant thing for experimentalists because that simplifies, especially in solid state, their implementation. These codes have a high noise resilience, which means that they have a threshold around 0.7%, which relates to a fidelity of 99.3. The threshold of a code, if you don't know it, it means the maximum amount of noise that this code can tolerate. If you have more noise than that, your error correction basically is useless and you are doomed. So the error correction theorists, we try to give you more threshold and the experimentalists try to make the things less noisy so that everything's better, basically. And some other thing is that we know how to operate with this code like efficiently without losing the error correction properties, which is important because otherwise we wouldn't have like memories and we want to operate over the protected codes. What's the disadvantage of these codes? They are very bad in terms of coding theory. They always encode a single logical qubit, and in order to increase their protection, you need to increase the lattice size. So your protection, which is called code distance, increase linearly, and your lattice size increase quadratically. That implies that you need a lot of qubits in order to protect your single logical qubit, so only to have one. And as an example, I give you for the error rates that the Willow processor of Google, so the one where they demonstrated error correction, in order to have a single logical qubit that is able to have a million error-free operations. So that's what I mean by this mega qubit thing, which is some fancy word that the error correction people invented. You need 1,700 physical qubits, only to have one. So in Donostia, we have a big quantum computer, let's say, of 150 qubits, but so this number is bad, let's say. So what can we do? So in the first world, what we did is to study how to reduce these overheads by using something called bias noise, which is relevant for certain qubit platforms, such as semiconductor spin qubits, ion traps, or MV centers. There are more, but well, and they have different biases. The bias of the noise means the ratio between the probability of having a dephasing error versus bit flips or bit and phase flips. Okay, and this relates experimentally with having much longer T1s than T2s or, well, the T2 is different. You have Ramsey, IKUR, we have heard Inigo talking about that, so well. But this ratio, basically. So you have more probable, the qubits are more probable to experience dephasing errors than other kinds of errors. And this simplifies the error correction protocol because you can focus on this predominant error source and use less resources for the other ones. And this has been studied in the past for some noise model, which is called code capacity, and I will go to that now. The code capacity noise model is a toy model for error correction, which assumes that all the quantum gates that you use to implement your error correction code are ideal, and only your qubits experience errors. This is very optimistic, okay? Because in reality, everything that you put in your quantum computer is noisy, and you have to consider that, but the first works done in like 2021 or so on for these bias noise things consider this model. And here you can see how the threshold of the code, specifically this is called the XCCX code, okay? You can see here, which is a modification of the surface code. It's just the same lattice, you just change the operators that you use. You can see that when the bias of the system increases, so this proportion of C probability versus X, your threshold increases like crazy. So that means that you can have like much better error correction. Okay, what happens in reality? We need to implement these codes in like reality, so the gates are noisy as well. So all the operations that we use are noisy. So here we study what happens when you actually implement something in, not in reality because we didn't do it experimentally, but with the most advanced noise model that you can. So whenever you do that, every gate in your system, you model it as an ideal gate followed by a noise channel, and that thing should somehow resemble what happens like experimentally. So here we have the concept of a bias-preserving gate. So a bias-preserving gate is a gate that you can model as the ideal gate followed by a noise channel that maintains the bias that I was speaking about before, so these ratios. So this is not always the case. For example, for the CNOT gates, which are very important for error correction because they are used in order to extract the syndromes, you cannot construct a bias-preserving CNOT gate. That's proven in this paper if you have two-level system qubits. So the intuition for that is that when you apply a gate, you are not doing some instantaneous thing, you are applying certain pulse, right? So, for example, a CNOT can be written in this way. This is not an X, this is a V, sorry, which is this V, is the drive that you put. And you see that in the target qubit, you have this X that is like, the control node thing. So while you apply your pulse, since this operator anti-commutes with the dephasing errors that may occur predominantly, they are transformed. So you effectively lose this bias. And that's the reason why this happens, this fact that you cannot construct a CNOT gate that preserves this property. There are some exceptions, like cut qubits and neutral atoms, that there is theory where you can prove that you can construct this kind of bias-preserving CNOTs. They are very interesting, of course, because they would allow very low overhead error correction, but they are very challenging to implement experimentally, as far as I know. These proposals are from 5 years ago, and there is no experimental proven yet, so it seems that it's not that easy. Okay, so we took a twist and we say, okay, what other gates we have in this to extract syndromes? So for example, we have the CZ gate, and we thought like, okay, the CZ gate does commute with the predominant noise because it's a rotation on the Z-axis. So we say, okay, we can use this gate to extract it, but the important thing is not to have a CZ gate, but also like how you experimentally implement this gate, because there is a concept called native gate, which is the native interactions of a system, and then you can build over those native interactions to contract the gate you want. So imagine that you construct a CZ gate using a CNOT, then that thing would not preserve the bias. So the important thing is that these CZ gates are like, let's say, enabled in a bias-preserving manner by means of the native interactions. So with this table with some technologies that may have this bias-preserving CZ gate, and which ones no. And then we went to simulate what happens with this. So this is the threshold of the code under circuit noise, so everything is faulty. Whenever you consider that the CZ gate is not constructed in a bias-preserving manner. So you can see that the threshold does increase a bit, but almost nothing. However, if you do it in a bias-preserving manner, your code threshold shoots up, basically. So in order to understand these things, that means that we go from a threshold that is a 99.34 fidelity in terms of gate fidelity to a 98.73 fidelity. So we are making, let's say, use of this property that is of these technologies in order to have a much better fidelity for experimentalists, as I was mentioning. And this is basically, let's say, for free in sense, you just need to construct the interactions correctly with enough fidelity. And as I say here, many technologies could already be sub-threshold if they think about the error correction this way, because, for example, these purple lines is the threshold of the code I was mentioning for symmetric noise, and you see that many technologies like, silicon or whatever are very close, so you can do many things. But if you consider this bias, you go here and you are very deep sub-threshold. So you can start doing some cool experiments if you have enough qubits. Okay, and finally, we computed the footprints, which is the amount of qubits you need to reach third-time fault-tolerant regimes, as I was mentioning in the first slide with the surface code. So we did it for the Willow error rate, because it's like, let's say, state-of-the-art in surface codes. And we can see that whenever we increase bias, we reduce like the amount of qubits we need, like 75% even for over all the regimes we consider, which are like million operations, billion operations, and trillion operations. And so the conclusion of this work is that basically you can save a lot of qubits by just making your interactions bias preserving in a clever way, let's say, if you think about this way. Okay, and now I will speak about the second work I mentioned. It's a bit in another, let's say, direction. So you may have heard, about this paper that IBM published like last year, I guess, where they proposed the use of something called quantum low density parity check codes, or LDPC codes, in order to reduce or cut the cost of quantum error correction, okay? And you can see here, like, you can save up to like 90% of the qubits required to do error correction using these novel techniques. So what are QLDPC codes? QLDPC codes just mean that you have a sparse parity check matrix, which relates the interactions that you need. So this thing needs to be sparse. The surface code is in fact a LDPC code because it has a sparse like interaction profile, if you think about it. It does have a lower qubit overhead. For example, the code that they named gross code encodes 12 logical qubits with 144 physical qubits, which is a much better rate, like 1/24, compared like these things that were 1/1000 for the surface code. It has great tolerance to circuit noise, so for the realistic noise models, it does have a similar threshold as the surface code. And fault-tolerant operations are now pretty well understood because of many works done the previous years by people in IBM, MIT, and wherever. They generalize some techniques from surface codes, basically. Then there is the issue of non-local connectivity. So you lose by using these codes in terms of like friendliness for experimentalists, because you cannot just do a plane as for the surface code. You now need like long-range interactions in between certain qubits, and that's experimentally challenging, at least for superconducting qubits. So IBM is trying to develop something they call C-couplers that allows these long-range things. But there are other technologies that may already be using these things, like neutral atoms. You can move the things, so you are not as constrained about connectivity as superconducting qubits. So they may start doing things with it. And the thing we targeted for this work is the decoding part. So the main decoder for LDPC codes is called BPOSD, which I'll briefly explain later. And the problem is that it's too slow. It has qubit complexity, which for error correction is too slow. And it is hard to integrate in specialized hardware like FPGAs or ASICs, so, which is integrated circuits. So that's where the niche we try to explode, basically. So what's the decoder? The decoder is a classical algorithm which is in charge of estimating which errors occurred by means of the syndromes, which are the partial information that you measure from the quantum computer. So whenever you implement an error correction code, you do certain interaction, you go measuring, and you start getting a stream of classical data that you need to process in order to know which errors occurred. So there is a very stringent requirement for this. Your decoder should be faster than the syndrome extraction round. So each round in a superconducting processor is like 1 microsecond. So your classical algorithm for decoder should be like faster than this, which is very, very stringent. For surface code, there are a lot of decoding algorithms, but not for general LDPC codes, which there is this belief propagation because LDPC codes actually come from classical coding theory for communications. Our phones use this stuff. And the thing is that belief propagation is a decoding that is basically a message passing algorithm. So you can think about like a neural network, so 2 layers of things that are connected, a graph, and you exchange messages around them in order to perform inference, okay? So it is very fast because it has linear complexity, and it's easily integrable in FPGA and ASIC because it comes from classical, so all satellites and phones and stuff have this stuff already implemented in them. What's the main disadvantage? So the thing is that it works very bad in quantum because of this effect called degeneracy, which is very important for code construction. Actually, like the best quantum codes exploit this fact. The thing is that then the decoder gets confused when this thing happens, this belief propagation at least. So that ends up in requiring this post-processing thing, which is called OSD, which implies order statistics decoding, which basically does, it takes some information that belief propagation gives to you, and then attempts to do some matrix inversion thing. That's why it's cubic, because you need to perform Gaussian elimination. Okay? So here you can see how bad belief propagation is for the surface code. This in the left is just belief propagation. So you can see when I increase the lattice size, the code gets worse, and it doesn't even have a threshold. So this belief propagation decoder is very bad by itself due to this degeneracy thing. Whenever you add this post-processing thing, you see that you recover a very nice threshold, and it's comparable to matching. Okay, for the surface code, you would use matching, which is a very famous decoder. But this is just an example of why BP is so bad. Okay, so what did we propose? This degeneracy thing, in terms of the algorithm of BP, what happens is that you have loops in your graphs. These loops are very bad because it makes the information like to be trapped in those. So, but belief propagation is assured to converge, which means that you can always get a good solution if your graph doesn't contain loops. So our main idea is basically to run belief propagation. If it doesn't work, we go to our post-processor, which we call ordered tunnel forest, and it's based on the fact of looking into the tunnel graph, in this graph where you attempt inference, the most probable tree-like graph, okay? And this can be done efficiently by means of this algorithm called Kruskal, which is almost linear in time. And then, when you have this tree, you can run belief propagation again on that, and you get a solution. This is the main idea of the decoder. So these are the results we got. For the solid lines is BPOSD, so the baseline. Okay, thank you. And the dashed lines is the BPOTF, okay? And so you can see that we match the performance of the state-of-the-art decoder, basically. And then we timed, in this laptop, the time that it takes in order to decode. So the X's are BPOSD, and the circles are our decoder. So you can see we almost get like an order of magnitude in many cases. This is for two different error rates. So the more error rate is more demanding because you get more complicated syndromes in order to decode. Okay? And basically we are proving that our decoder has promised to be a real-time decoder. So basically this is what I wanted to show. We proposed this algorithm that has proven almost linear time complexity. And one of the things is that these timing results have been done, as I said, using my laptop. So we are using a version of belief propagation that is not parallelized fully. So in reality it's n squared. So let's say that these points for us should go lower. But basically you need to implement all this stuff in an FPGA or whatever if you want to see the real thing. But basically it's that in terms of, if you go to implement it, it should work better even. Basically, that's what I wanted to say. And it's easily, in principle, to be implemented in like specialized hardware because it's mainly based on belief propagation, which is already know how to do. And yeah, so basically it's like belief propagation is very bad, and our solution is like basically to use it more, you know. So thank you, and if you have any questions, please go on.
Thanks. Josu. Questions?
Hi.
Hi.
Nice results on the second part, but I'm going to ask about the first one.
Yeah.
How do trap ion platforms overcome this no-go theorem that you presented?
You mean it's not trapped ions, it's neutral atoms?
Well, neutral atoms, whatever, yes.
Okay. I'm going to say first one thing. I'm not a physicist, so my knowledge about this may be a bit limited. But as far as I know, the cat qubits exploit the fact that they are trying to use like infinite dimensional things. So then you go into some, different physics than two levels. In terms of the neutral atoms, I don't have it very clear. They speak about something that is called very high nuclear spins, and they have all these diagrams of their, things and explain the way they do it.
I mean, neutral atoms, they probably use other states to do the CNOT. Mm-hmm. They may not be strictly two-level system, but then the last question follows. When this no-go theorem refers to it's impossible to have CNOT gates, for two-level system qubits. It means for the qubits themselves in the sense of the information they're encoding or the two-level system that they are realizing the qubits.
Okay, so this is a bit oversimplified. With two-level system qubit, I mean the qubit like you have two levels and you want to apply a CNOT. You may have superconducting qubits, you have more like levels, but you aim to do a CNOT in this level. So that's what I mean by two-level system qubit here. This no-go theorem goes beyond that, and also it says that if you use, let's say, more levels to encode a two-level qubit, so you can do singlet triplet encoding, for example, in spin qubits, you still cannot do this. So you need to go to some, let's say, infinite dimensional thing. That's why I don't really understand very well this thing. I never went into the physics. There is a PRX paper on that by the Looking Group that I can share if you guys want. And I don't understand the physics, so I didn't went very much into that. Yeah.
Thanks for your talk, Josu. I would like also to ask about this and to understand better why people focus so much on the CNOT gate that it cannot be obtained in a bias preserving manner. I mean, I think I understood your argument. Why that since the Mormon-Sorensen, for example, interaction does not commute with the Z noise, etc. What happens, however, with single qubit gates, like X gate, for example, does not commute with? Why don't you talk with this X gate?
That's a very good point. So, yeah, in fact, we do have like single qubit gates because I do have like a lot of backup slides because, you know, this is like some Frankenstein presentation. I've been pulling everything to the back. But, well, this is the XCCX code for anyone interested. So, you do use H gates in order to, I mean, we do use single qubit gates such as the Hadamard gate in the simulations that we are doing, for example, to do this. Because if you have a control C gate, I mean, let's go to the beginning first. I don't know if I have those slides though. No, okay. So let's see this, okay? You see here an X and here a C, right? This green thing and this orange thing. These are the checks, okay? So they relate to the stabilizers that you want to measure. So you need, so for example, if this qubit experiences a C error, that thing anti-commutes with the stabilizer and you want this check to activate. If it has a C error, this doesn't trigger this thing, but it does trigger this other stuff, okay? So in order to do something 2D, in terms that we are able to detect all the possible errors that you have, you need things that anti-commute both with X and with C, okay? So you end up needing having, in order to do that, you use CNOTs, okay, that you can do like this thing. So whenever you have a CNOT, here, if I have a C here, this C will propagate here and activate my check, okay? If I have an X here, nothing will happen in principle. If I have an X here, this will propagate here with a CNOT. So if you want to only, let's say, encode the things using CZ gates, you still need these Hadamards in order to make it anti-commute with the noise, yeah? So we still do that. We focus too much on the 2-qubit gates because they are the ones that, first, they are the noisier ones, and second, yeah, I think that may be the main point, yeah.
There is an assumption that the 2-qubit, there is, I guess, the assumption implicit that the 2-qubit gates are more of a problem than the single qubit.
Yeah. But for our simulations, we don't use that kind of model because it's symmetric. So these guys are also more, let's say, no, they experience the same noise, these gadgets, in the model that we used. Okay. One thing that happens as well is that from these, the locations in which these gates are, okay, do not propagate errors that are bad into other locations of the circuit, okay? I know this is a bit complex and without the actual circuit it's hard to see, but whenever you have, imagine a CNOT and then another CNOT like this in the same check, if this guy puts me an error here, this can propagate to other qubits, okay? So the places where the Hadamards or the single qubit gates are do not allow these kind of propagations. So they are not as important in the extraction schedule for this code. But, and as you mentioned, these Hadamars that we are using, they do not have bias. So they are not bias preserving as well. So they are also problematic. And that's the reason that we see this saturation, you know? It saturates a lot. So in the code capacity, you see like this is like 1,000 and you're still going up. And we get a lot of saturation. And that's because our model is not perfectly biased. Because we do still have some imperfection like Hadamard gates, things that are transformed in ways that we don't want, and some gadgets that may not be able to have this property, but we still see that you can get a lot out of it. So the main point of this is like, you know, we are all, I mean, at least me that I like theory, you are like, okay, I want to do bias, I want everything to be biased, you know? And it's the approach of the cat-qubit people. They say, okay, I can do, the cat-qubit people, what they are trying to do is to suppress exponentially the bit flips, so to generate T1s that are hours, and have T2s that are short, so there is this exchange there. And then since they can have these bias-preserving things, also for the single qubit gates, then they would forget about the bit flips. I won't correct those. But so people are like, okay, if you don't have this CNOT, then this is boring, I don't want to do it. So our main point was like, okay, if you go to practice and you want to save qubits, you still can, even if the things are not perfect. Yeah.
Okay. Okay, so we thank Josu again, and we thank also all the speakers of this first morning session.